I mean, behind all of us is independent increments. Independent increment more or less independent, so that we are adding the independent estimator to improve the variance, and then plus smoothness of trajectory. Because if I don't have smoothness of trajectory, I cannot localize in time. Because just like imagine each day have complete different volatility, how can I average them? Right? I mean, it doesn't make any mathematical sense. So this is, in other words, this quantify is the smoothness. That is, at the two time point, S and T, this as looking as a function of T, not as as a factor rate. So this would be Lipschitz with some kind of Q. Q is nearly a half. I repeat the same many times, nearly a half. And that if this mu and sigma is nice enough. So this is really off on diffusion. Diffusion theory basically says that if I have 4 p moments plus a little bit delta on it exists, then the trajectory is guaranteed to have this Lipschitz type of continuity. And this K, of course, is a random quantity because it's a random variable, so expected value less than infinity. But anyway, so these are the details, but basically saying that smoothness can be guaranteed if data generating process R and S here is small enough, that's bounded or, I mean, have moment conditions, okay? Okay, so now state domain estimator. I mean, a lot of people in Berlin school here has done, I mean, millions of contributions to that. So, so let me just talk very quickly on that. So what I remember is the difference and suitably standardized. So then you can write as a drift plus volatility in just an Euler approximation scheme. So if you either ignore this drift term, or if you want to estimate it, you're welcome. Estimate it will give you a little bit benefits. Then you could construct the estimator based on this, just based on localizing in state domain. Then you got an estimate of that. So I'll talk in the next draft. Now, people may say, well, how about second order difference? I mean, you know math better than first order difference. And of course I did that. Richard Standen in 1997, Journal of Finance, wrote that. I mean, this is the second order difference, for example. I mean, for estimating the drift. You could also have second order difference for estimating the volatility, okay? So if I construct this way, then it can easily prove by using the infinitesimal operator that the expected value of this linear combination of the past 3 days, right? I mean, 2 delta, and t, or I mean, depending on where you say past or future, whatever. So it would be of second order. So approximation reduced to second order, and Richard Standen conclude that higher order difference because of delta squares should perform always better than lower order difference. And so I just take fun and calculate what is the variance. So the variance is increased by a factor of 2.5. So your benefits of second order, I mean, of approximation error is coupled by your variance increases. So it's the same way if you estimate the volatility, the factor 3 here, 2 here is replaced by 3. Now how about your third order approximation? You could also do third order difference here to make this is cube. Then the variance here, not a 2.5, I think maybe 7 point something. So anything you gain by approximation error would be seriously damped by statistical noise. So this, I mean, there's a inflation of variance exponentially. There has a study, I mean, in the paper by myself and now my former student. Now she established herself in the Korea. So all I'm trying to say is higher order difference not necessarily give you any gains. And if you don't believe mathematics, I could do this just numerically, okay? So this is the Treasury bill from 1976 to 2003. That's about the time maybe we published, I think, this paper here. Right? So everything, publication, if you see the data where I start, is usually the time I write the paper. Right? So here is based on the first order difference for estimating volatility. And this is the standard error associated with the estimate. This is based on the second order estimator. You can see second order approximation, the variance here is about the square root 3 of that. So this is the evidence that by going to higher order difference, while gaining you unknown bias, for sure it will increase a known factor of variance. And the variance so large, the benefit is small. So this really approves to a lazy approach. People say, okay, let me use first order difference. And people may ask you, why you only use first order difference? Now you say, oh, there are some theories justify using higher order difference doesn't provide any gains. It's not my laziness. So for this reason, for estimating volatility, I'm going to talk today is based on Euler approximation schemes, because any higher approximation schemes, you'll pay a large price in variance, but the bias gain, how much is unclear. Okay, so now with that understanding, then the problem here is become very simple, right? So this is a non-parametric regression model. You have your observed y, you have your observed x here, and you want to estimate covariance matrix. So all you need to do is apply smoothing in state domain. So let me take the cross product, I ignore the drift term, and the fit cross product, I fit a local linear to it. This looks like a complicated one. It's really a linear model, linear in the state domain that you are localizing around this x0. So this is linear in that state domain. So you do a local linear estimator for each product elements, and you minimize this with the kernel weights here. So kernel weights basically just like Gaussian density with the variance h. H control the window size of Gaussian density. When h is very small, you are talking about localizing very small in the local domain. So at the end of the day, local linear estimator, if you really write it out, is a weighted average of your standardized difference process, and plus local linear weights here explicitly written down below. But if you really want detailed formula, but probably the detailed formula is not that important. It just so this basically says, if we go back to this picture, basically saying, okay, I just take all data point in this window, and I compute the sample covariance matrix on that, and the only difference is I put weights on sample covariance matrix. That is the closer data to 6.5% of my today's interest rate, the higher the weights I receive. The further apart outside, I receive smaller weights. So this is really all a mathematical expression, a local linear estimator saying that. So let me not detail to any of those and explain those pictures. So now what is the dynamical weights? So the dynamical weights I choose, which will be justified mathematically, that is the proportion of effective number of data points in the state domain and the effective number of data points in the state domain, and this is the effective number of data points in the time domain. So what is unknown here? Unknown here is really tau, depending on what the tau you use, right? So the tau, what is the tau? Tau determines the local local time domain smoothing. So what is the tau here? Just refresh. Okay, this is exponential weights, and this is the tau. So determine how much you weight it down. Okay, and what is the and the other one is the bandwidth h that you localize in state domain, and this is sorry, I go fast here. The h here. So h here is reflect n times h is the number of data points, because I have h and I have window size n. Now this capital N is the total number of data points in these 40 years history, and this little n is the data point I use to do time domain smoothing. So I exclude those time domain smoothing I exclude those local, in other words, in my smoothing here, or maybe this picture, the same picture is easier. So I exclude, in state domain smoothing, I starting from here, so only use history. I don't use the same piece of blue data. So I exclude the blue part of data. So that's why you see there's a minus n there. So capital N minus n is because of my exclusion explicitly to not use those data points already used in the time domain. So this is why you have this. So for example, if you, and this px is the local time, how much, how often the interest rate visits 6.5%, right? So this is the local time of this invariant density of this RT. And in my implementation later on, I'll take n explicitly equal to 2 years, okay? So 104 weeks, okay? And lambda, I'll take JP Morgan's suggestion that is equal to 0.94, and of course I could back solving this tau, right? So tau is given. I'm just lazy in choosing bandwidth, and H will choose to minimize some of estimated prediction errors. Okay, so let me talk about performance first, and then see whether it's necessary we talk about mathematics. So the performance, I have the true covariance matrix, I have my estimate covariance matrix, so you need a kind of loss. So one kind of loss is the Kullback-Leibler distance, discriminant information between two Wishart distributions. So this is called entropy loss. And the other one, probably people will say, let's take quadratic loss. That's just Frobenius norms between these two, sum of square of all entries, right? So this is the Frobenius norm. So this would be the second loss. But this can only be done if you are doing simulation. Then you know what is the true sigma, right? So you could compute this true sigma, and you could compute this. Now in the real data, who knows the sigma? The sigma is something I want, right? So you find a proxy of this sigma, and this is what people usually, and this is the first one used on in simulation. So, you find a proxy of the data. That is, you use these yi and yi transpose to proxy of this true sigma. Right? So we know that yi transpose is plus a lot of stochastic errors that over there. So if you compute the expected prediction error is always equal to stochastic noise, the noise level, and then plus estimation error. As everybody have done prediction knows very well that the prediction error usually is, and stochastic error is usually an order of magnitude bigger than estimation error. But it's not prediction error in this situation of my interest. Is this guy of my interest, right? These two guys really of my interest. What is the difference between my estimated volatility to the true volatility rather than the prediction error? I predicted nothing there. So because imagine this is 10, this is 1, okay? So it's 11 total, right? So now if this 1 is reduced to 0.5, is a lot of improvement in my estimation efforts of volatility precision. Now this basically say 11 to 10.5 ratio. So a very small improvement in PE, prediction error, not price to earning ratio, I'm sorry. So in prediction error, it means a large improvement in the estimation error. So with this kind of scale clear, we can move on. So let me explain one more. I know it's a little bit confusing here. So let's say the prediction error, stochastic error is 10 times larger than estimation error. So this is 10, this is 1. Okay, so my ultimate prediction error I could get is 11. So now suppose I have a very small idea, reduce estimation error, that is volatility estimation error reduced by half. So this would be 0.5, but stochastic error would be still 10. So I'll be from 11 reduced to 10.5. You may be thinking, well, you reduce small amount, but reduction of small amount means a huge reduction in the accuracy of volatility matrix. Okay, with this understanding, then you'll know the scale of improvement. Okay. Now, how do we do simulation model? So I try to be as close to financial, financial modeling as possible. So we basically use Duffy's essential affine models. So we think that the short-term rate in the risk-neutral world is generated by CIR process, right? So, so this is a square root Feller law we have. And so this is the state variable. The short-term interest rate is a linear transform of this state. So I'm talking about one-factor model. You could extend to two-factor or three-factor models here. So is this. So with these models, then for the zero coupon bond paid in maturity of tau. So what is the value of this? Is the bond price will be discounted. Discount by short-term interest rate, right, in the risk-neutral world. So this would be the price of zero coupon bond at time t, maturity in 3 months, tau, right? Okay, so this is the standard. Now the beauty of affine, essential affine model is that you could compute this, ugly expectation explicitly, okay? And this ugly expectation is given by this exponential form, okay? It's A tau, depend on time to maturity, B tau, and your conditioning on your state variable st now, right? So everything is conditioning on st now, t here, right? So depend on st state variables. So this is another Duffy or Duffy. This guy is in Berkeley. I know these two names are very close, Duffy. and Kahn. Okay, so okay, so anyway, so A and B solve the following ordinary differential equations. So for the parameter we give, just to give you an idea what B looks like, this is the time to maturity. B increase slightly with time. And this is because there's a negative term here, right? So increase means decrease if you so decrease slightly, doesn't decrease much. The bond value certain decreases fast as tau increases. So this function A tau decreases very fast as time to maturity increases, okay? Okay, so with a bond price, of course, bond yield just the log of your bond price, annualize it, right? Divide by tau, annualize it, so it's equal to this. So if you look at this model, I mean, Duffy and Kahn certainly realized that there's deficiency of their modeling, and the deficiency is that yields are perfectly functional related. Okay, that is, if I give me 1 year terms interest rate, I should be able to solve this ST, and from this ST and A tau, B tau, I should be able to determine 3 years, 5 years, 20 years. So they are functionally related. So in order to make it more realistic, they add in noise. So they say, okay, this is the theoretical one plus Gaussian noise added to it. And at the end of the day, I have my process like that. So another beauty of this affine model is that I'm able to compute the conditional variance of my YT process, with noise, can be computed explicitly so that I know what is the sigma t in my simulation. Okay, so now having said that, it's a lot of details, but let me say that, okay, so I generate 500 time series. Each of those consists of 1,200 weeks of weekly data, and I reserve first 900 for state domain estimation, and then the rest I do time domain estimation for outsample forecasting. And with this model, you could generate as much data as you can. So we generate tau equal to 1 month, 2 years, 4 years, 6 years, and 8 years. Okay, so we do this. And the parameter we are using here are not cooked by myself, cooked by Caradito, who was here, my colleague, and Bob Kimmel was my former colleague. So thereby fitting treasury data, they're getting all the parameter I want here to do simulation. So in other words, my simulated parameter is took from their estimate parameter to fit into the treasury bills. So the paper was published in Journal of Financial Economics. So this is the 500 simulations. So this is entropy loss, and this is quadratic loss. So what I'm indicating here, this is the time domain estimator over those 150 outsample period. So this has mean square error that big, and I have exponential. This is the state domain, and this is aggregation. So you could see aggregation error. Error in terms of entropy loss is certainly small. You cannot be much smaller. I think the smallest is possible for minimizing, combining two independent estimators is, I think it's 2 or something like that. You have an upper bound. You cannot improve upper bound by increasing 2 pieces. And this is just the standard deviation of the simulation error over 500 simulations. And this is the same thing that applies to time domain, state domain, and aggregated one. So time domain and state domain in quadratic loss is harder to say. Some periods time domain is better, some state domain is better, but once you aggregate them, the aggregate estimate is always better. Okay, so this is a point-wise loss. Now, if I could also summarize this into a different ways. So in doing each simulations, I have 150, let's say, entropy loss. So I just averaging those clap those into one number. And now I do 500 simulations, right? So now I do, here I just plotting you now I do 500 simulations. So this is each simulation will give me one average error like that. So I just averaging those, I getting one number in my one simulation. So I could do this 500 times, and I got the distribution of those average prediction error, an average entropy error, and this is the time domain error, This is the state domain's error, and this is the aggregate domain error. So you can see aggregate domain error is always smaller. Even the worst scenario is better than the best scenario of both estimators, which is intuitively that we would expect to be true. And this is the using prediction error. No, sorry, this is using the entropy error, and this is using the prediction error. Now, what I'm plotting here is, what if you change a measure? I mean, a change of measure, that is, I replace, let's say, entropy error here by prediction error here, right? This is also a measure. As I said, prediction error is dominated by Stochastic error. So if I look at these picture again, I mean, you may look at the three methods about the same, because I just adding, I mean, a huge number, just like what I says. The estimation error is in the order of 1. The prediction error, I mean, the Stochastic noise is in order 100, right? So 100 plus 1, of course, now making everything is very small. So this is the plotting of, again, this is a prediction error. This is time domain, state domain, and aggregate domain. So we cannot see much the difference, but but this is the domain that we are really interested in, the true volatility compared with your estimated volatility. So we are not really interested in Stochastic noise here. So this is just a noisy version. Imagine this noise is, this estimator being blows up by a factor of 1,000 or something that make everything looks the same. Right? So each of these distribution times 1,000 or something make it like the same. So, but at least this gives us a kind of scale. That is, if prediction error can be, so this helps us for calibration. So this is time domain, this is state domain, this is aggregate, and so this is time domain, this is state domain, I think this is aggregate domain. Yeah. So if I have small improvement just in this small order of magnitude, as in this picture, I mean these three, right? Time, state, and aggregated. So if I have a very small improvement in prediction error, you should expect to see a large improvement in the domain of your true interest. And why I'm keep emphasizing on that, because when you analyze the real data, all you do is prediction error available to you. So all you can see is on this domain. But now I'm doing this simulation to demonstrate you if I have a small improvement, like this, a small slight improvement, you mean you have a huge improvement in your estimated volatility, because the volatility matrix of your interest is not the noise of your interest, okay? So with this understanding, so I'll apply to real data quickly. So so this is, and I claim that time domain and state domain are nearly independent. So in simulation, it's cheap, right? I could verify this. So I take equally weights among bonds that I simulated. Okay, so and then I simulate 500 times. So I could always compare the pairwise correlation between these. Among 150 outsample forecastings. So the correlation between time domain estimator for these equally weighted bond portfolios is, this is the sample correlation, this is the confidence interval, this is the 0, and this is 0.1. So anyway, so they are pass all reasonable tests to be independent. So this basically showing that practically time domain estimator and state estimator is asymptotically independent. Okay, so this, for simulation, as I say, you have simulate 500 times, so you can always compute those kind of correlation. Now let me apply to empirical data. So I have 3 months, 2 year, 5 year, 7 year, 10 year, 30 years bond. It's just the same way that I do. I use first 900 as my testing sample, as my training sample. So I learn state domain estimator like that and fixed. And then I use the next 2 years as my forecasting as my outsample. And so, we do testing sample 150. And these next 2 years is to learn, to build time domain smoothing. And we also apply this to exchange rates data. And so here is, so now for the real data, all I'm able to calculate is the prediction error, because there's no entropy loss there, because I don't know the true sigma t. There's no project loss there. So this is the time domain error. Forget about -3 here, right? This is state domain error, and this aggregate domain error. So there's a small improvement here, right? And the currency that you also see small improvement, 1.65, 69, 70, right? So small improvement there. So this looks quite desperate. I mean, I don't improve much, but if you look at the simulation example, 8.25, 8.25, 46, 50. So this is the simulation example I showed you a moment ago. So simulation example says that it looks so similar here, but there's, I mean, in the real domain of your interest, you have huge improvements here. Right? So this is the domain of interest you are like. So now by doing calibration, I have small, I mean, improvement here on about the same order of magnitude as this improvement. So I would expect if there's an oracle or there's a God tell me that what the true sigma is, then in the true sigma domain, my improvement should be also looks like that. So in other words, the improvement is quite large. It's not small. So, so this is the real data examples. So now let me mind you just by quickly scan through some asymptotic theories. Okay. So the asymptotic theory is basically looks like this. Okay. So let's say if you give me a symmetric matrix. So you define a vector of A is just stacking each column down, right? So this would be, and VECH is just you do the lower triangular of symmetric matrix of that. So then exists a projection matrix PD with elements 0 and 1, making these are exact equal. Under this kind of smoothness condition, and if sampling frequency is go to 0 this way, then you have asymptotic normality of time domain smoothing, and this is explicit compute here. This basically tells you the effective number of data points. This is the scale of volatility matrix you need to have. So this is a long matrix that we have here. And similarly, in the state domain estimator, I will have the same results, exact the same lambda x, lucky enough, and this is the effective number of data points I will have here under some kind of mathematical conditions, okay? And finally, you say, okay, if you aggregate time domain and state domain estimator, they are asymptotically independent. That is, if you put in these two as a two-dimensional process, right? This is one vector of very long, very, very long, and this is another vector of very, very long. Putting them together, there will be a joint asymptotic normal with correlation go to 0. So therefore, if you aggregate those together, that will be go to normal. And then the optimal ways you are choice here is minimizing apparently the blue quantity here. The blue quantity here only depends on effective number of points in state domain, effective number of points in time domain, and that's it basically. And this is how we got the effective weights. Okay. And so let me conclude. I know that the time is up, because, so let me conclude is that for stationary processes, there are two domain law estimator for us. One is time domain, the other is state domain. So they provide two nearly independent estimators for us for estimating conditional moments. I mean, one is rely on continuity, that's time domain, that's why you localizing in time. The other is rely on stationarity, that's why you localize in state. You don't care whether it's 5 years ago, today and tomorrow, or today's today and tomorrow, because it rely on stationarity. And they can be aggregated to estimate a much better statistical performance. And they, of course, can be used to test against stationarity, just weak stationarity in time and so on. And I again just prove the concept that you can do this. Of course, you could use more complicated ideas, like Valadia was talking about, breaking state domain into a few pieces rather than one piece. You could also include more than one factors. Here I'm using one factor. You could including additive model or single index models to make technique more powerful. So if I have 10,000 man years, I certainly will be able to do all of those. But I have only one man year. Thank you. So that means I give a pretty good talk. Everybody understands. It means the lunchtime.
that is asking about someone chooses financial sales data. Your experience, whether it follows a taxonomy process or non-taxonomy process.
Yeah.
Your own judgment.
Right. So I assume it's a stationary process. Suppose it's not stationary, and you know the extent to which how it's non-stationary, so that you are able to aggregate information in the past to the future. I mean, stationarity basically say past and future relationship doesn't change, so that you could use that. So if you have non-stationarity, but somehow it's in a parametric form, so that you understand the past and future are changes, but you know how it changes, then I think the idea could still apply. I mean, in a very similar way. But then I need to assume how it is non-stationary. That part is, and I indeed also interested to see how this kind of thing can be applied to high frequency data. See, I do high frequency, I do this, but sometimes I just don't simply have enough energy to do both together. Because high frequency data now you have lots of state. We are now currently completely rely on time domain smoothing. You could also rely on state domain, or even localize in the volume or whatever. There are something that you could localize, and you could get another independent estimator and hope that we could improve the estimate.
More questions? No, then we take we come back.
Financial, fit adequately an asset. So for example, just give a very simple example to prove the concept. Does CIR model fit the short-term interest rate? Well, most people maybe here, of course doesn't. It's fine, doesn't, but I mean, can we show something that provides strong evidence? It doesn't. And now if you enlarge your own model, you maybe say stochastic volatility model, does it fit the interest rate model? So in this case, the null hypothesis is always very well, defined. Like for example, if I ask, does CIR model fit the interest rate? So the null model is CIR model. There's no ambiguity here. So you have three parameters: long-term mean and the speed of, what? I forget the speed of. Speed of mean reversion. Thank you, and the volatility, right, and the square root. So the traditional parametric way people will say, all right, if you want to test this, then let me embed this model to a bit larger model, right? So this one larger model is, the CKLS model, that is constant elasticity models, CEV models. So this would be like a power here. So then the problem becomes testing whether rho equal to 1/2 or not equal to 1/2. So in this case, then you could, then you could just do like a ratio test and you are done. However, there's a price, just like all things you have. We always trade off between, flexibilities and, estimability. So this way, if I have parametric model, both of those are very estimable because there are few parameters here. However, there's a cost of model misspecification error. So in order to make the problem easier, I use this picture as example. So suppose that I ask you, does age has any impact on income? Well, so if you think, okay, let's say null hypothesis is linear model with no intercept, right? So this, that is the age and income is not related. But somehow unknown to us, the age and income relation is quadratic. I draw in this way, but you could draw in actually more realistic like this way. As you're getting younger, your income getting higher. As you're getting older, you decrease again. But now I'm just doing the reverse, the same thing. You could flip my picture. So if I do test linear hypothesis that beta 1 equal to 0 against beta 1 not equal to 0, and the true data generating process is like this, you will see that there's no strong evidence, right? Because the difference between those, if the data is quadratic like this, and if you fit a linear model, the slope will be 0. So you get to the wrong conclusion. So in other words, when you do specification tests, alternative is too small, you are in danger of making, the error to begin with. So implicitly in our assumption of somewhere in doing hypothesis testing, we assume that alternative model is large enough to include the true dynamics. So for this reason, I mean, if I ask a CIR model, one alternative model people would say, well, let's do non-parametric. That is, I'm not willing to assume that volatility has to grow in this power form, but just any function depend on your level of interest rate, sigma xt, and the mu sigma xt. Okay, so if I do that, then you may also complain, Professor Fan, how about if my model is not of this? Let's say it's more than one factor. This is basically one factor, Brownian motion determining everything in my dynamics. How about two-factor models? Then you also say my model is too small. But the concept here is null hypothesis is very well defined. Alternative, you have a lot of choice. So this is two. Now, how about the third one? Well, the third one is, what I'm trying to say is, okay, transition density, right? And I'm trying to say, whatever the test you are looking at certain aspect of transition density, mean or variance, summary statistics, cumulative distribution function. You are always using certain aspect of deviation. And since data generating process is governed by transition density, so it's most likely, most natural to say that let me test whether transition density is the same as transition density of CIR. So a quick test, what is transition density of CIR? Right, non-central chi-square distribution, right? So anyway, so we know that the transition under null hypothesis is non-central chi-square, and or some way, at least you could simulate it if you like. Just simulate enough data, you could get transition density correctly, right? And now if you're willing to compare transition density under null hypothesis, this in my specific example is non-central chi-square distribution, and alternative hypothesis is non-parametric distribution. Now, what is the metric I should use to compare the distance? And of course, people would say likelihood ratio would be most relevant, right? Because this is talking how far two distributions are about. If alternative is 10 times more likely than null hypothesis, I should, reject the null hypothesis. Okay, so this is, so in order to study this, so let me just enlarge my scope a little bit. So null hypothesis is a well-defined parametric family with transition density given by this, and delta is governed, like the sampling space, like time frequency, your observed data. So this usually implicitly given, there are some computational issues there, and there's approximation issues there too. So alternative hypothesis, you may say, well, is a non-parametric hypothesis like this, one-factor model. But then you also say one-factor model is not large enough. So let me just use, in general, transition density, alternative hypothesis, without specify the transition density under the alternative hypothesis. So now I have two guys at my discretionary. One is Wolfgang, who like parametric family, right, always, and the other is Yassin Aisa Halia, who like a non-parametric. I asked them to do, that is null hypothesis has more, has more chance, or alternative has more chance. So you could compute Kuiper-Leibler distance between your null hypothesis, implied transition density, and your alternative hypothesis, that is transition density without using any form, just implied by the data itself. And now if you put into those, the challenge is it becomes highly nonlinear because it's a likelihood ratio is a Kuiper-Leibler distance between two, and also the data are dependent, not independent anymore. And even under null hypothesis, even though my colleague Yassin is extremely enthusiastic about his higher order Edgeworth expansion and still working on that, finding maximum likelihood is still a challenge for this in the general parametric family. Okay, so now the scope of my applicability. Now, if I do this, here's a picture summary. So parametric null hypothesis is always very well defined, like a CIR model. So it's a parametric in this magenta area here. Now, depending on extent to which that you like to believe your alternative. So one is that you believe CKLS, CEV model, so you are embedding your null hypothesis into a larger family of parametric one. So this is like this, okay? So CIR, and this is CEV, just replacing rho by, not equal to half by any numbers there. Okay, so this is a statistical modeling. And then you could say one-factor model as your alternative, right? So this is like this as your one-factor alternative. And then the last just one, of course, just say anything stationary, mixing enough, that could include one-factor, 20-factor, 100-factor models. So it's all included in this big space. So our talk today actually is more or less like a null hypothesis here, alternative is very big. So there's a penalty to this, that is the power of the test usually not as powerful as if I test null hypothesis here, alternative is here. So null hypothesis is here, alternative is here. I have done some paper actually published in JASA doing that kind of things, but the general I'm talking today is more mathematical challenge from here, jump to here, okay? Any questions so far, the introduction? So I don't want people to get lost in the introduction. Any questions? So how long do I have time? Oh, so it's more generous in the last one? Pardon? 2:30? Okay, I'll be a bit shorter. I know that people are all very tired. So as long as you can learn the story. Okay. Okay, so, so now here is our formulation. So this is the discrete sample with frequency delta. So to be lazy, sometimes I write delta equal to 1 because there's no time units here, right? So it could daily data, could weekly data, could be, 5 minutes data. So I just write as xi, okay? So the likelihood under null hypothesis, under this diffusion, stationary assumption will be given by this, Markovian assumption will be given by this. This is likelihood under null hypothesis. And this usually doesn't admit an analytical form other than 3 models, geometric Brownian motion, the OU process or Vasicek process, CIR models. We know very little about this. So as I said, Yassin Aissa Halia gave some Edgeworth expansions, making us possible to compute a few more order approximation. But otherwise, most people do just Euler approximation. So he did a bit more than that. So nevertheless, in our own experience, even with Yassin's help, Yassin doesn't like that, but every time I present that, he says, is this true? I say, yes, it is true. Numerical implementation is still challenging to find maximum likelihood under this, this null hypothesis, okay? So now under the alternative hypothesis, I need to get the transition density. That is, all I have data is xi, a time series xi and xi plus 1. So we know that if I conditioning on xi minus 1, then I localize in xi around this y. So this is a kernel just like Gaussian density with variance h2. So as h2 go to 0, this is approximately just conditional density. So in other words, conditional density is really a regression function of a nearly delta function on xi, right? So this is a transform of that. So this enables us to get a non-parametric estimation. So now this is your weights. This is your y random variables. And this is your localized in x because you need to condition it on x. So this is a kernel function you put down here. So in that paper, we do local linear weights. So it depending on n. But explicitly, it really depends on this. So this is very explicitly being given. So there are a couple of variations of our publications on how to do transition densities, more explicitly, but this detail is not important. Then the next one, people may ask, how do we choose bandwidth? Believe me or not, very few, I know there's a lot of study by the school here that how to select bandwidth, but nevertheless for it's very few for doing transition densities. So in our paper, we are doing very heuristic, saying, okay, you set H2 like a normal reference in bandwidth, and you select H1 like a non-parametric regression, because once H2 is given, is a non-parametric regression problem, so there's a bunch of methods you could use. And there are other heuristical rule or thumb methods and so on. So the first one that I'm aware it could be consistent is a kind of cross-validation methods. So I mean, mathematical writing like this, but let me just not go detail to it. And Peter Hall and his collaborators using this even to select the dependence variable of conditional densities. That is, conditional on 10 variables, which field variable would be important, and so on. So let me not go to that. So if you like traditional statistics, you could also say, how about let's base on transition distributions? I mean, transition distribution is just a cumulative distribution of transition densities, right? So in this case, you could just say, okay, I put the indicator function here, and then again, I put the kernel weights here. So now this is a slightly rewriting of the same thing that I wrote before. This is just a kernel regression on this indicator function. And if you really like, it's really a special case of transition distribution. You are integral with respect to, you integrate this with respect to y, and then let this h2 go to 0. I think that would be exactly the transition distribution. Okay. So transition distribution is a transition density integral. Let second smoothing parameter go to 0. So okay, so this is, so you got two estimators. Now the construction of test statistic become easy. So you would say like ratio tests, right? So this is non-parametric implied, likelihood under the alternative hypothesis. This is parametric implied transition density under null hypothesis. And you put certain weights at the region you have very small data or unreliable data, you put the weights here. And because this everything there is quite complicated, and most people will say, okay, if you do Taylor expansion under null hypothesis, this should be close to chi-square test statistics, is T1, like a chi-square test statistics here. And we also did that. Actually, proving from T0 to T1 is quite difficult. Actually, it will maybe take 20 pages to prove that. And I know nobody in mathematical statistics or financial econometric or in econometric group would love to see 20 pages proved just to show from here to here. So why don't we just starting directly from T1? T1 is a test statistic itself. Okay, so, and then T2, you could just say I take no weights here. Probably my square here shouldn't square on the denominator. It doesn't look like I need a square there, but anyway. Pardon? Oh, you agree, right? So I realize there's an extra square there. So this based on the like ratio test I don't do here, yeah. Yeah, you could, a Hellinger distance of similar problem, you could do that, yeah. I haven't done that. Again, if I have as many years as you have, that you have 20 people working 15 hours, so you have many years then. Okay, yeah, no, okay, no, I'm joking, come on. So, okay, so now you could also do the transition distribution based, right? So this would be the difference between distribution implied by non-parametric and by the parametric, and you could do that. So this is really regression of indicator function on xi. So this will give me T3. And then you could do, for transition distribution based estimation, you could do bias correction. That is, you hope under null hypothesis, my estimator should have no bias. And this is possible. Actually, the early work was done by like Hadler, Mammon, and who else? Only two persons, right? I mean, this was in 1993 Annals paper. And you could apply similar idea to do bias correction here. Basically saying that if you want to test hypothesis that these are equal, why don't you think that they are, the difference between those are equal to 0? Once you think the difference between these are equal to 0, then you are doing the regression of this indicator subtract by this. You're putting a hat here that you do just a non-parametric estimator of the difference. Then in this case, it's really a pre-whitening idea. Under null hypothesis, because null hypothesis thing is equal to 0, so there will be little bias of root and consistent. So this is the same idea as spectral density estimation. You do pre-whitening, so the same kind of idea here. Okay, so therefore you could do bias correct estimator and so on. So maybe I'll not talk any detail on this. Okay, so there's a lot of related literature. So given the time I have here, I'm not going into any detail, but one thing that I would like to implement here is a very simple idea by Yong-Mil Hong Haitao Li in 2005, published in Review of Financial Studies. So their idea is very simple. If null hypothesis is correct, then I apply the transform of my transition distribution to it, then my transformed random variable Zi should act like independent uniform distribution, right? So this is, for univariate case, we all know that. So this is called Rosenblatt transform. So going to the credit where credit is due is Rosenblatt transform, maybe in early 50s, am I correct? I think historical accounts like that. Okay, so now then Emil's and Hong and Lee's idea is say, okay, let's see if Zi is really testing, if Zi is, null hypothesis becomes Zi is uniform, alternative say it's not uniform. And of course, he want to taking, then you could say bivariate, the pair should be uniform on the square. Or you could say trivariate uniform on the cube, right? So he apparently choose bivariate on the square in order to account for zero correlation. So in this case, he need to do kernel density estimation with boundary corrections and to deal with boundary effects, which are also sensitive to the test statistics. Okay, and there are empirical likelihood methods I'm not going to talk about here since I'm not presenting there. So let me talk 2 words about Rosenblatt transform. So I mean, Rosenblatt transform, if I do bivariate, I will have bivariate test statistics, estimating of my uniform density, and subtract by 1, and putting an L2 norm. That's what Hong and Lee did based on bivariate. Goes back to Berlin? Yeah. Sure, everything has.
Because what you receive here is a Kramer from Mises type distance.
Right.
And from Mises was Professor.
Okay. Yeah, okay, so that's true. This is, so the whole testing here is, so the only difference is that for Mises didn't use non-parametric. Other than that, everything is, yeah, you are absolutely right, yeah. So now you could say, okay, why don't I just make life easy, right? So my students say, okay, well, I just wanted to take univariate and see if my univariate Zi has a uniform distribution, right? So this is really saying that this is really like a coming from Mises test you are talking about for the univariate case. So this is uniform cumulative distribution function subtract by uniform cumulative distribution function. I mean, and or if you like, you could do even bivariate just to mimic the Hong and Lee. So once you are looking at this way, the whole universe becomes very simple. You could construct as many tests as you like, and you could compare null hypothesis with alternative hypothesis. Okay, so one nice thing is of the last 2 test statistics is that you don't really need to choose any bandwidth. You don't need to deal with any boundary effects. You apply it and you get some results. Right? So we'll include those in our power studies. Okay. So by the way, I mean, in the paper I'm talking here, we do not include jump diffusions. Actually, in our revision, we did include jump diffusions. I mean, the procedure is not much different. And now how do I get the p-value? Well, I mean, if mathematically you could justify that, then you could just do bootstrapping. That is, you assume that MLE give you the model, and that is, you draw the sample from null hypothesis with MLE give you theta hat. So you just draw the sample from this, or more generally, I mean, if you have transition density that you already specify under null hypothesis, you could generate from this. And now you could just compute test statistic many times by using simulation and using empirical quantile, the simulated quantiles to replace that quantile, so you get a p-value. So it's easy to implement. Now you may ask me, is it justified? I mean, then that basically means, is this sensitive or important? I put a different theta hat here, my null distribution would change a lot, right? Because if I put MLE there, people say I could put the non-MLE there. It's also a possibility to be a null hypothesis. So then I need to prove that the asymptotic null distribution is nearly independent of those theta. So this justifies why you could sample from sample from this parametric value theta hat here. So this phenomenon, I'll call it as a Wilks phenomenon. And this is really the theorem showing that, okay? So it's ugly, but I hope it's correct too. so basically say T1, which is the chi-square distance between non-parametric and parametric hypothesis. If you subtract by its mean, the first order, because I localize in H1 and H2, so I have H1 divided by H2 degree of freedom, thinking of I have a rectangle, divide this into bin without H1, and divide this into the bin without H2. So you have asymptotically with the constant here doesn't depend on Newton's parameter. The constant here doesn't depend on Newton's parameter, and sigma 1 here all depend on the kernel you smooth on x direction and the kernel you smooth on y direction, and so on. So this is basically saying that Wilks phenomenon holds, that the asymptotic null distribution we simulate from here doesn't appear any theta value in my asymptotic null distribution. So if I translate this into a more familiar form that you are familiar to you, basically it's a Wilks type of result. Asymptotic null, I mean, like a ratio test, suitably normalized by a constant, looks like this. Okay, it will be a asymptotic chi-square distribution with degree of freedom looks like this. And degree of freedom is exact H1 and H2, because H1 and H2 is the rectangle that I partition x direction using H1, partition y direction using H2, and so the total number of squares I will have, or rectangle I will have, will be of order 1 over H1 and H2. Okay, so nice pause. So now